Hello and welcome back, my fellow path integrator. Today with a very beautiful calculation we're going to calculate the photon sphere, so the radius at which a photon is able to circle a black hole. This is kind of crazy because black holes actually suck in everything, even light, but there is a way how light can orbit around it circularly. So how are we going to do that? Well, black holes, that's the realm of general relativity, so we have to deal with metrics, but it's quite simple. We're going to deal with the Schwarzschild metric. The Schwarzschild metric is given in an infinitesimal form and in spherical coordinates, so we have c squared times 1 minus 2mg divided by c squared r. Here m is the mass of the black hole, g is the gravitational constant, c is the speed of light, and r is the distance from the singularity to wherever in space, times dt squared. Then we have minus the whole thing, 2mg divided by c squared r, now inverted, dr squared. Now I need to make this a little bit smaller because we're talking about spherical coordinates, so we are missing two coordinates in our four-dimensional space-time. We're missing r squared sine squared theta d phi squared minus r squared d theta squared. Alright, so this is our Schwarzschild metric, and what we're going to do now is we're going to abbreviate it a little bit. So we're going to define the Schwarzschild radius, so the event horizon, as 2mg over c squared, and this means that 1 minus 2mg over c squared r is equal to 1 minus rs over r, and that we can define as alpha, to keep it short. And we will apply another trick that theoretical physicists love to apply in long calculations, and it's just setting the speed of light to 1, because it's a constant, and in the end we can just do dimensional analysis to check where we need the speed of light to keep up with the right dimensions. Alright, so with all these abbreviations, our Schwarzschild metric now looks like this. So we have alpha dt squared minus alpha inverted dr squared minus r squared sine squared theta d phi squared minus r squared d theta squared. So next thing, how are we going to find out about the circular orbit of the photon? So let's imagine a black hole. The black hole is this blue thing here, and now we have a photon orbiting it, so let's have a circle here. First of all, we have a radius r, and this is the angle phi that the photon is traveling. How do we actually determine the circular orbit of any particle when we talk about classical physics, Then we determine it by looking where all the forces are equal, so to 0, so where all the forces that are acting on the particle are equal to 0. And what we also learn from classical mechanics is that the force is equal to minus the derivative of the energy with respect to the distance. In this case, the distance is given as r, so this is the force. So if we find out what the energy is of the photon circling the black hole, we can also find out where is the exact point where all the forces acting on the photon are 0, so where the derivative of the energy with respect to r is 0. So as you'll see, we will deal with a simple calculus problem, finding the extreme values of the energy of the photon traveling in the Schwarzschild geometry, in the Schwarzschild spacetime. So how are we going to do this? We're going to apply a method that is also very common among theoretical physicists, and it's the Lagrangian method. So the Lagrangian for a particle traveling in a space-time, in any type of space-time, so any metric, is minus the mass of the particle traveling times the square root of ds squared over dt squared, where dt squared is the infinitesimal coordinate time, so it's the time of a resting observer. So all we need to do is we need to plug in this metric here into this formula, and then we will get the Lagrangian. And the Lagrangian is a function that contains all the information that we need about a physical system, and from the Lagrangian we can easily determine the energy of the photon or of any particle. As you'll see, we are dealing here with the Lagrangian for any type of particle with an arbitrary mass. You also see that the mass cannot be set to 0 because a photon has a mass 0, but setting the mass to 0 here would mean that the Lagrangian is equal to 0, and we cannot work with that. So first we need to handle it as if we're dealing with an arbitrary mass that is unequal to 0, and then in the end, when we have the energy, we will have a nice expression where we can just cut out the m and we get a nice expression for a particle moving in the Schwarzschild geometry with 0 mass. Okay, so now we just plug in the metric into this formula for the Lagrangian. So we have minus m times the square root of alpha times dt squared over dt squared, and this we can just abbreviate to 1. Then we have alpha inverted times dr squared over dt squared, and this can be abbreviated to r dot squared, and in the same manner r squared sine squared theta phi dot squared minus r squared theta dot squared. Alright, now we have to think about the movement of the black hole, not the movement of the black hole, the movement of the photon around the black hole again, to simplify this Lagrangian a little bit. Because this is the Lagrangian for a general movement of a particle in the Schwarzschild space-time. So it could be any type of orbit, doesn't mean it needs to be circular, it could be hyperbolic or parabolic, you know. So we need to do some abbreviations and simplifications to simplify our Lagrangian. Well, let me show you what I mean. So here is the black hole, and we have the photon traveling around here. So maybe we'll get a perfect circle here. Wait a second. Bam, here we have a perfect circle, and the black hole is roughly in the center. Alright, so we have the photon traveling around here, and we already said that this is the angle phi and this is the radius r. Well, the radius r of the circle remains constant, so r is equal to constant, and this means that r dot is equal to 0. So this part of the Lagrangian, we can already drop that, which is amazing. So the next thing that we're gonna do is take a look at the Lagrangian, at the orbit of the photon, but flip the whole perspective such that we have the black hole like this. We have it flipped on 90 degrees, so 90 degrees, and the orbit of the photon around the black hole looks like this. It's in a plane, and we can just choose this plane to be the pi over 2, so the 90 degrees plane. That's just a convenient choice. It can be any angle, but if we plug in theta equals pi over 2, then sine squared of theta will just equal 1, and this will simplify our Lagrangian even more. The most important thing though is that theta is constant. As you'll see, for the whole plane, for the whole movement of the photon around the black hole, it's always in the same theta plane. So theta is constant, which means that theta dot is 0, so we can drop that part from the Lagrangian as well. So in the end, our Lagrangian looks like, let's write it in yellow, L is equal to minus m times the square root of alpha minus r squared phi dot squared. Alright, and now we can determine the energy of the particle. So how do we do that? Well, we just apply the formula for the energy dependent on the Lagrangian. So the general formula is the sum over all the coordinates. Then we have the time derivative of the ith coordinate times the Lagrangian, which is dependent on those coordinates and on the time derivatives of those coordinates, and we take the derivative of the Lagrangian with respect to the time derivative of this coordinate, and then from the whole sum we subtract the Lagrangian. In our case, the Lagrangian is only dependent on phi dot, which means that the energy is simply phi dot times the derivative of the Lagrangian with respect to phi dot, and then we subtract the Lagrangian. This is very easy to calculate. We just need to calculate the derivative of the Lagrangian with respect to phi dot first, and this is d with respect to d phi dot. And then we plug in the Lagrangian, and the Lagrangian has just been minus m times the square root of alpha minus r squared phi dot squared. So we apply the chain rule, and what we will get is m r squared phi dot divided by the square root of alpha minus r squared phi dot squared. And that we plug in into this part here, so we just multiply the phi dot with another phi dot, so we get phi dot squared. So we have E is equal to mr squared phi dot squared divided by the square root of alpha minus r squared phi dot squared minus the Lagrangian, and the Lagrangian itself is minus m, so plus m times the square root of alpha minus r squared phi dot squared. And now we extend this part to a fraction with the same denominator as this part of the expression, so what we will get is m r squared phi dot squared plus m alpha minus m r squared phi dot squared divided by the square root of alpha minus r squared phi dot squared. And here, this is quite easy to see, this part and this part, those two, they cancel each other out, so we are left with a simple formula for the energy, which is m times alpha divided by alpha minus r squared phi dot squared. So now we just need to get rid of the phi dot, so this is the energy. Now we just need to get rid of the phi dot, and in order to do that we are going to introduce a new constant of motion, and this is going to be the angular momentum, because the angular momentum is as well conserved as the energy. The angular momentum, which is capital L, is in Lagrangian mechanics defined as the derivative of the Lagrangian with respect to phi dot, and we already calculated that. So the derivative of the Lagrangian with respect to phi dot is the angular momentum, which is a constant, so it's constant at all times, and this is just m r squared phi dots, not phi dot squared, just phi dot, divided by the square root of alpha minus r squared phi dot squared. So what we want to do is we want to write phi dot or phi dot squared as an expression dependent on the constant term the angular momentum, which is a constant term. So what we're going to do is we're going to square both sides of the equation. So we have L squared is m squared r to the power of 4 phi dot squared divided by alpha minus r squared phi dot squared. Now we can rewrite this equation as m squared r to the power of 4 phi dot squared divided by L squared is equal to alpha minus r squared phi dot squared, and then we have alpha is equal to m r to the power of 4 divided by L squared plus r squared, and the whole thing multiplied by phi dot squared. So this we can also rewrite as phi dot squared times m squared r to the power of 4 plus r squared L to the power of 2 divided by L to the power of 2. And now we just rewrite the whole thing in, so we have an expression for phi dot squared, so phi dot squared is alpha divided by m squared r to the power of 4 plus r squared L to the power of 2 divided by L squared. So this we can further rewrite, so what we're gonna have is L squared alpha divided by m squared r to the power 4 plus r squared L to the power of 2. And this is phi dot squared. And we have our energy given, which is m alpha divided by the square root of alpha minus r squared phi dot squared. And that's what we're just plugging in now. So we're going to take this thing and plug that in for phi dot. So what we get is that the energy is m alpha divided by the square root of alpha minus, now we have L squared R squared times alpha divided by m squared R to the power of 4 plus L squared R to the power of 2. And this we're going to solve by extending this here to a fraction with the same denominator as this. So we have m alpha divided by the square root of alpha m squared r to the power of 4 plus alpha L squared r to the power of 2 minus, and now we have L squared r squared alpha divided by m squared r to the power of 4 plus L squared r to the power of 2. And those two, those two, they cancel each other out. So in the end, we're left with m alpha divided by the square root of alpha m squared r to the power of 4 divided by m squared r to the power of 4 plus L squared r to the power of 2. And this we can further rewrite as m alpha times m squared r to the power of 4 plus L squared r to the power of 2 divided by, now we take the square root, so we have square root of alpha times m times r to the power of 2. So the m's, they cancel each other out. And the alpha divided by square root of alpha just becomes a square root of alpha in the numerator. So here we have square root of alpha. And this is our expression for the energy. And now we are finally at the point where we can say, okay, this is our expression for the energy, and now we set m to 0. I'm sorry for this. I'm just talking for too long. So now we set m to 0, which means that the energy is the square root of alpha times L divided by R. And this is our expression for the energy of a photon traveling in a circular orbit around a black hole. And all we need to do now in order to find the exact position, the exact radius at which this is happening, is we need to take the derivative with respect to r, set it equal to 0, so we find the point at which all the forces acting upon the photon are equal to 0, and then we'll just solve the equation that we get for r, and we will get the radius of the photon sphere. So I'm really excited. Let's go. Let's take the derivative and set it to 0. So we have the derivative of the energy with respect to r is the derivative with respect to r of L times the square root of alpha times 1 over r. So L is a constant, but the square root of alpha is not a constant because alpha is dependent on r. So we have L times the square root times the derivative with respect to r. Now we plug in 1 minus rs over r divided by r. And we need to take the square root out of that, of course. So that's what we need to take the derivative of from. Let's rewrite this expression. First, this square root divided by r. So we can rewrite this as L times the derivative with respect to r of the square root of 1 over r squared minus rs divided by r to the power of 3. Now this is quite easy to take the derivative of, so all we get here is 1/2 times L times minus 2 r to the power of minus 3. So this is the first derivative here with the chain rule, plus, and then we have 3 r to the power of minus 4 times rs, and then the whole thing divided by the square root of 1 divided by r squared minus rs divided by r. And that whole thing should equal 0. Alright, so we can drop that part here, of course, because we just multiply both sides of the equation with it. So we are left with, after dropping this of course as well, because this is also just a constant, so we have minus 2r to the power of minus 3 plus 3r to the power of minus 4, rs is equal to 0. So 3r to the power of minus 4 rs is equal to 2r to the power of minus 3. So now we can put it to the other side, so we multiply both sides with r to the power of 3, so we have 3r to the power of minus 1 times rs is equal to 2. So we have 3rs is equal to 2r, and this means that r is equal to 3 over 2 rs. So r is 1.5 times the Schwarzschild radius. So if this is the black hole, so this here, I don't know, maybe I'll zoom in a little bit. So this is the black hole and this is the radius r, then the black hole, the photon radius is at a distance of 1.5 times rs. So this is where the photon can orbit the black hole. Well, we are at the end of this video. I hope you enjoyed it. I really love doing the calculation with you. I hope you could also learn something new. That's always nice. If you enjoyed calculating this with me, please leave a like. If you haven't subscribed already, think about subscribing. I'm gonna do a lot of those videos in the future. And leave a comment. If you want me to go deeper into some topics like Lagrangians or metrics and general relativity, let me know. So far, so good. Have a nice day, have a nice evening, have a nice morning, have a nice week. See you in the next video. Goodbye.